Good afternoon, everyone. I'm Meng Jin from Northwestern University in Xi'an, China. Today, I'm going to share with you our recent work titled FlipTracer, Practical Parallel Decoding for Backscatter Communication. This is a joint work between Northwestern University and Tsinghua University. Backscatter technology provides benefits of energy harvesting and low-power communication, which make it attractive to many applications. Most of these applications involve a large number of deployed tags to transmit large volumes of data. Therefore, how to fully utilize the channels and enhance the network throughput turns to be a very important problem. To solve this problem, parallel transmission is explored in many recent works. They allow the tags to transmit in parallel, and the collision will be decoded at the reader side. To achieve this version, we need a parallel decoding method to decode the collided signal. Before talking about parallel decoding, let's first look at the signal when only one tag is transmitting. Since tag echoes its data by reflecting or absorbing the camera waves, so there are two magnitudes in the time domain. We use a threshold to decode the signal. If we look at the IQ plane, we see two sample clusters representing the two backscatter states. Now we have two tags. Since each tag has two states, so we will have 4 states in total. These states represent the combined state of the two tags. Now the problem is, how can we identify the combined state of the signals? Theoretically, channel coefficients of the tags are stable and can be linear combined when collision occurs. That's to say, the four clusters create a parallelogram in the IQ plane. So, if one of these clusters is identified, such as LL, it seems that all the other clusters can be further identified based on their locations on the IQ domain. However, in practice, we observe both dynamic and irregular signals in the IQ domain. For example, if the tags are moved, the positions of the clusters will change with the dynamic environment. And also, when two tags become too close to each other, tags may backscatter the signals from other tags. So in this case, we can observe the nonlinear dependency in the collided signal. At last, in a low SNR scenario, noises from the environment will increase the radius of the clusters, which incurs overlap between clusters. So we cannot even separate different clusters in this case. Clearly, it's challenging to identify the clusters based on their locations on the IQ domain. So to solve this problem, some more recent works combine the time and IQ domain information to identify the clusters. Specifically, by leveraging the reader's capacity to sample at a much higher rate than the tag, we can extract each signal edge. If all the tags have stable bit duration, we can map these tags to the flipping of the nodes. Then, using the IQ domain information, we can finally identify the combined state of the collided signal. However, underlying this method is an assumption that all the tags have very stable bit durations. That's to say, they require that the clock of the tags have very low drifting rate, which is, however, unrealistic in today's backscatter system. Due to the low-cost design, the clock in the backscatter tags typically have very high drifting rate. As we know, to separate the signal from different tags, the clock drifting rate is required to be lower than 200 ppm. However, based on our measurement, 70% of tags drifting rate fall between 40,000 and 68,000 ppm. The above experimental result motivate us to think about a question that how to identify the combined states of each cluster based on such dynamic and irregular signal. Our idea is to use the signal's transition probability between clusters. We find that although the positions of the tags, positions of the signals are dynamic and irregular, signal's transition probability between different clusters are highly stable. Indeed, a higher transition probability between two clusters implies the higher similarity between their corresponding states. For example, the transition probability between cluster LL and LH is much higher than that between LL and HH. Then let's look at the reason behind. In practice, signal's transition between different clusters is caused by the flipping of the tags. So since flipping of different tags are interleaved most of the time, so signal transitions are usually caused by only one tag. That's to say, signals usually transfer between clusters whose combined state have only one different state. Of course, in some real case, two tags may flip their state at exactly the same time. This leads to the signal transition between two clusters whose combined state have two different states. However, the probability for such signal alignment is very low. Let's look at an example. If the tag transmits at 100 kbps, the reader sampling rate will be 250 times higher than the tag speed rate. So, in this case, the probability that the two tags flip their state at exactly the same time is only 1.2%. That's why the signal usually transfer between clusters whose combined state have only one different state. We term such cluster pair as neighbor clusters. So, if we can identify the combined state of one cluster, we can then identify the combined state of its neighbors and then its neighbors' neighbors, and finally, we can identify the combined state of all the clusters. Now we take the three-tag collision case as an example to explain how FlipTracer works. Our first target is to construct a graph to connect all the neighbor clusters. We term this graph as one flip graph. The nodes in the one flip graph are the sample clusters, and if two clusters are neighbor clusters, we will build a connection between them. To construct the one flip graph, we first cluster the received symbols and calculate the transition probability between each two clusters. Then we use the transition probability to find the neighbors for each cluster. And finally, we will get the one flip graph. However, one problem we face here is how to handle the false connections in the OFG. Indeed, we can identify the false connections based on the fact that if all the connections in the OFG are correctly formed, there will be no loops with an odd number of nodes in the OFG. For example, in this three-tag collision case, we can see loop with 4, 6, and 8 nodes. And however, a false connection always form a loop with an odd number of nodes. So we can avoid forming false connections by detecting such abnormal loops. Now we have the one-flip graph, and the next target is to identify the combined state of each node on the graph. First, we need an anchor node, whose combined state is known. We consider the node LLL as the anchor node, because we can always identify this node when all the tags are being charged. Then we layer the nodes based on the distance between the nodes and the anchor node, and then we identify the combined state of the nodes layer by layer from the anchor node. Now we introduce how to identify the clusters. Clearly, the nodes on the first layer have only one edge state. We can identify their combined state as HLL, LHL, and LLH without loss of generality. Then we identify the combined state of other nodes based on their neighbors on the upper layer, whose combined state are identified, like this. Finally, we can identify the combined state of all the nodes. Then, by checking these combined states, FlipTracer outputs a sequence of H and L states to represent the transmitted signal for each tag. This binary sequence can be decoded by the conventional single-tag decoder. Now let's look at the performance. We implemented FlipTracer on the USRP N210 software-defined radio, and we use this reader to read the programmable tags. We compare FlipTracer with two methods. The first is CB, which identifies the cluster based on their locations on the IQ domain. And the second is backgroup, which combines the time and IQ domain information to identify the clusters. We first compare the throughput achieved by different schemes for different number of types. We can see that the throughput of FlipTracer is very close to the upper bound, and the gain of FlipTracer is big. In the 5-tag collision case, FlipTracer is 2.5 times better than backgroup and 15 times better than CB. To further investigate the maximum throughput of FlipTracer, we then keep the number of tags as 5 and increase the bit rate of the 5 tags from 100 kbps to 600 kbps. The results show that the maximum throughput that FlipTracer can support is concurrent transmission from 5 tags at 500 kbps. We further conduct experiments under different environments to see the impact of practical factors. We can see that FlipTracer is robust to both poor channel condition and dynamic environment. So in conclusion, FlipTracer is the first practical effort to achieve highly reliable parallel decoding, even when the signal is highly dynamic and irregular. To do so, it provides a new graphical model that translates the transition probability between signal clusters to the similarity between their corresponding states. It is implemented on a USRP N210 based RFID reader and evaluated through experiments conducted in different environments. So thank you so much for your attention. I'm happy to take your question.